begins, though, I wanted to introduce a staff from the University of Formation has done a lot. And welcome. Thank you for joining. So, yes, I'm not going to spoil Alexandra.
Thanks, Russell. So, hello everybody, you all know who I am, and you just heard who I am if you didn't. So, big thanks to my committee who's here today. So, Russell and Wei Chun, where's Wei Chun? There's Wei Chun. Sebastian, Todd, and Tom McGath. And, did I get everybody? I hope I got everybody. Okay, if I missed you, please speak up. No, I got you all. Okay, good. Okay, so, I've been studying young stars in the Gum Nebula with Russell White, as he mentioned, and today I'm going to tell you about how a high radiation environment may affect these young stars. First, let's start with an overview of star formation. Generally, you'll start with a big collection of gas and dust, like really, really big molecular cloud, and you'll let self-gravity do all the work. It'll condense everything down into these dense cores, and eventually, in some of these dense cores, you'll get stars in the middle of them. So those are protostars. This is the phase in which we expect the stars to be rotating very rapidly as they've condensed down from a very large size to a very small size. Any angular, we okay? Okay. Any angular momentum that the original large cloud has would be turned into a very, very fast rotation speed in the compact protostellar object. So we also expect vigorous accretion at this stage, as this is when we expect the star to be gathering most of its mass. Give that a bit of time. Some of the gas will go away, some of the gas will flow onto the star, some of the rest of the gas, with the remaining angular momentum, will go into the disk around the star. This gives us what's called a T-Tauri star. These stars are generally 1 to 10 million years old, and they give off a very distinct signal. They generally have strong H-alpha emission. So that's a really good way to pick them out. Some regions where we see this large molecular cloud type of star formation is in Taurus Auriga and Rho Ophiuchus, and some other places. It's a pretty common way to form stars. We're going to be concentrating on these two stages of this whole picture today. So the mostly T-Tauri stars, but possibly one protostar. We're also going to be looking at a different way of forming stars. So if you have a lot of gas and dust, great, you can just form stars with gravity. But what if you don't have very much gas and dust? We still see star formation in regions that are more diffuse and in clumps that are small. Something that can help it along is what's called triggered star formation. If you have a hot O star nearby, or even a B star, just giving a lot of radiation, that'll provide enough extra energy that it'll actually help even a smaller clump of gas collapse into stars. This is seen in, for example, Upper Scorpius and parts of Orion. And also in the region we're studying today. So this little object here, let's take a closer look at that. A good place to look at triggered star formation is in what's called cometary globules. What is a cometary globule? It's a lot like a regular Bok globule, which is a dense cloud core associated with star formation, but these are formed near big O stars. So the radiation that's falling on these globules is so strong that the gas tends to evaporate away from the ionizing source, the O star, and that'll actually give it a comet-like shape. You really only see these in a few places. One of them is in the region that we're studying right now, which I'll get to on the next slide. Just a quick note before I go off this slide. This is actually a star inside a cometary globule. We're actually the first to spectroscopically confirm one that's inside a cometary globule. And it makes sense. It's like a Bok globule. It just has a cool shape. It still forms stars. You're going to hear a lot about CG30 IRS4 as we go through this presentation. Okay. So where's all this happening? All this is happening in the Gum Nebula. This is a diffuse H2 region that's in the southern sky. It's in the constellations of Vela and Puppis, and it's in the galactic plane. Because it's in the galactic plane, it's quite understudied. If you go and look at Wikipedia, there used to be like 2 paragraphs. It has 3 because I just added one because it bothered me that there are only 2. I literally just did that. Yeah, I did that like yesterday. Yeah, I was. But I was making sure everybody else knew a little bit more about it too. So I couldn't resist, I had to. So yeah, 3 paragraphs on this in Wikipedia. It's understudied, it's a bit of a mess. It's in the galactic plane. But with the coming of Gaia, we're actually able to now disentangle some of what's going on in this region. So it's a great time to study this region. One thing that's very, very important, it's only 350 parsecs away. That's closer than Orion. So if there's star formation happening there, that's great. We should really be looking at this region a lot more. But I have dibs. Let's go ahead and zoom in on the Gum Nebula. Okay, so it's an H2 region. It does have some very hot stars in here. We see here Zeta Puppis all the way up there, Gamma 2 Velorum. Those are both O stars. And then here's the supernova remnant, the Vela supernova remnant. That probably used to be an O star. So lots and lots of radiation energy in this region. Besides just ionizing the gas here and making an H2 region, it's also formed this ring of cometary globules, all marked by these little diamonds, labeled with the little numbers. The Gum Nebula is home to at least 32 cometary globules. There are a few in other places. You'll see some in Scorpius too, Upper Scorpius. But there are a bunch of them here. So this is a really, really good place to just study a whole bunch of possible triggered star formation events. And yeah, that's what we're doing. We specifically looked at all the way up there, CG30, that little blue region by CG30. Let's go ahead and zoom in on that. There we go. So all these stars, they're marked with various symbols. The blue ones are the ones that we're going to look at right away. These orange ones we're going to look at a little later in the talk. We actually take spectra of these stars marked in blue, and we only have photometry for the rest. Same for the pink one over there. Okay, so what makes these stars special? The 10 stars highlighted in blue were first studied by Pedersen in 1987. They were picked out because they had strong H-alpha emission. That's a really good sign of that they might be T-Tauri stars, as you may recall. It's a good sign that they have a disk, and they might be accreting. So we've actually submitted the results of this study to APJ as of October, waiting to hear back. Really hoping they get back soon, but we'll see. And there's the title. A big goal of this study was to determine, are these stars really young? And also, are they accreting? We also want to look at, are they related to each other? Are they related to the cometary globule CG30? And then we derive something that's called the accretor fraction. And that's just simply, you're going to count up all the stars in that region that you've studied that are accreting, and then you're going to divide that by how many stars you studied in the region. So it's a good way to study how many of these still have disks, how many of these are still accreting, right? Because one would imagine that if you're in a high radiation environment, that number may be affected, right? Because radiation can disperse, it can disperse gas, possibly disperse disks. We want to check that out. What we did was we studied those 10 stars, just the 10 blue ones, with Keck, one of the largest telescopes in the world. It's 10 meters across. It gives very, very detailed spectra. We used it on the red end of the optical range because that, of course, includes H-alpha, good gauge for the accretion properties, and lithium, which is at 6708 angstroms. That's a good gauge for how young the stars are. Here's a look at those spectra. I think they look very nice. Some of these, this is not even, a lot of this isn't even noise. Those are features, all right? A lot of features in those areas. So here are some regions of interest. Also, you can see 6 stars here, each of their spectra going across. These are 6 of them. There are another 4 down here that you're going to see in just a minute. I've highlighted some regions of interest. On either side, we have the atomic lines, mostly of calcium and iron. These are nice because they help you figure out what temperature the star might be, what is its spectral type. They're particularly strong in K stars. Then in the middle, we have TIO bands, which are molecular features. These are particularly strong in M stars. And as you might see right away, we have a lot of M stars in this sample. We have a few K stars too. It's just M and K. These are young, so that's really all we have. Okay, what else do we have? This is a gravity-sensitive line. We don't do a lot with it in this study, but it's sort of nice to see. We expect these, because they're young, to be a little bit puffy. And here, this we expect to really see in young stars, lithium. In a main sequence star, it would just be flat. You wouldn't see much of anything for a low-mass star. But when it's young, as you can see, we see a lot of lithium. In fact, they all have it. All have lithium there. Okay. So you can learn a lot from this high-resolution spectroscopy. One of the first things you can get is, as I already sort of mentioned, the temperature of these stars. Because, well, it's atomic physics. Which absorption features are the strongest is going to be directly affected by the temperature of the star. So hence we get all the temperatures and the spectral types. We get this by comparing our young star spectra. Here's just an example. This is pH alpha 14, marked in blue. We compare those to well-studied spectral standards of same spectral type to the young stars. Yeah, I know. Some of you are saying, wait a minute, this one's a dwarf and this one's a young star. How does that work? Yeah, okay. It'll introduce a little bit of error. There should be, we're expecting for temperatures an error of maybe 100 to 300 Kelvin. That's not too bad for our purposes. So we do this, we move on. Something else interesting you may notice, though, is all these features in the young star look shallow compared to the spectral standard. Why is that? Turns out there's a very good reason for that, and it's accretion. This shallowing of all these spectral lines is called veiling. This happens because as gas flows onto a star, it's going to heat up and give off a lot of extra light at all wavelengths, especially blue wavelengths, but really all wavelengths, especially across the optical range. So if you do that, all the features will be filled in a little bit. This is something we can quantify, which is, and we will get to that. It's called veiling. Okay. First, we're going to get the lithium. So, as you may already know, lithium fuses at a much lower temperature than hydrogen. It can fuse at about 3 million Kelvin, whereas the hydrogen, you have to wait till you get to 13 million Kelvin. So, lithium's really easy to fuse. What that means is, especially for convective stars, lithium will be depleted in the first 10 to 20 million years for an M star. Okay, so that's pretty quick. That means that if you're looking at an M star and you see lithium, it's probably very young. In fact, you can pretty confidently say, so you saw all the lithium in these spectra. We conclude that these 10 stars are probably younger than 10 million years. Good ballpark. Okay. What about their accretion properties? So here's all the H alpha. This is why these 10 particular stars were first selected to be studied, is because they had strong H alpha emission. And yeah, so they really do. H alpha emission is associated with gas being in front of the star, basically, between you and the star. It's being lit up by the star, and it's giving off it's giving off that light, the Balmer series in this case. If it's broad, that's a Doppler shift, so that's associated with fast gas motions. A lot of that gas is going to be flowing onto the star, or onto the disk, or really both. Yeah, possibly just onto the disk for some of these, though. You may notice we are actually measuring the width not at the continuum, which is really rather ambiguous. Like, where does it start, where does it end, who knows? We're doing a much easier thing, which is we're actually measuring it 10% of the peak height above the continuum. Why? Because it's easy, see? So what that means is because it's so much less ambiguous, this is actually a much better test for are the stars accreting, are they non-accreting, are they classical T Tauri, are they weak line T Tauri, which is non-accreting. This is a much more robust test than trying to figure out, oh, geez, where does the emission start, right? So we do it this way. And from this test, question? Oh, heck. I don't know, like 1,000 or more sometimes. Like, it's really, really tall. It's so tall I never really bothered to check, but that's my ballpark answer just from having dealt with it. Yeah, pretty tall. Okay, anyway, so from this test, the 10% above the peak width, we have found that of these 10 stars selected specifically for their broad H-alpha emission, 8 of these appear to be classical accreting T-Tauri stars. The other 2, maybe not. Maybe the gas is just flowing onto the disks. So that's okay. But remember, that's only 10 of them, right? There are still there's actually a total of like 21 stars in the region. Some of them were those little orange squares. Those we only have the photography tree for. They were actually selected in a different way. So there are some selection biases here, and we'll talk about them. Okay, what else can we learn from our high-resolution spectra? We can get velocities. So we can get radial velocities, how is the star moving through space. We can get rotational velocities, how fast is the star spinning. And we can get veiling, which is that filling in of the spectral lines due to accretion that I mentioned. Okay? So we do that. We have a nice catalog of standards observed in the same way as our young stars. So we start with a standard, shown in pink all the way at the very top, that is of the same spectral type as the young star. And then we're going to take that standard spectrum and we're going to manipulate it very carefully until it more or less reasonably matches the young star's spectrum. And we're going to go through each of those steps. We measure the quality of our manipulations with a cross-correlation as we go. And also we have a least squares fit for the veiling. Let's look at each of those steps. The radial velocity, this is pretty straightforward. It manifests as a Doppler shift. So you just take your standard spectrum, move it around till everything lines up. And then you say, okay, that's how fast my star is moving. Here are the results, just quick results for these 10 stars. Bit of a range, but as you can see, it's color-coded. This is RA versus DEC, and it's color-coded for radial velocity. So right away, just from the color, you can say, these guys over on the left, maybe they're related to each other. They have a similar radial velocity. They might be moving through space together. Same with the guys on the right. Similar radial velocities, maybe they're moving together. Because that's what you expect. If stars are associated with each other, they should move through space together and thus have similar radial velocities. Okay. Now we get to rotational velocities. How fast is the star spinning? That's going to manifest as a Doppler broadening of the spectral features. You get this by actually measuring the width of your cross-correlation peak while you were sliding it along, trying to line everything up. These are T-Tauri stars. So they're already out of that rapidly rotating protostar phase. We expect their rotation to be, well, certainly much lower than that. A little higher than main sequence, but not wildly high. And that is what we see. We see a range from 6.3 kilometers per second to 27 kilometers per second. The sun, for reference, has a rotation rate of, what, 2 kilometers per second? Something like that. So not wildly high, but, you know, a little bit above main sequence. Interestingly, even that star, CG30 IRS4, is in the sample. It is embedded, but its projected rotational velocity didn't like go off the charts or anything. So that's interesting. We'll get to that later. Okay, the veiling. So this is that extra light that we get from accretion. We measure this by just adding extra light to the spectral standard and then renormalizing until all the features are sufficiently shallowed. Okay? So just so you can see, there's the formula all the way up there. R equals the flux of how much extra light you had to add, extra continuum, divided by the flux of the actual continuum. Okay? So for example, if you had a star that's accreting and it generates the same amount of light just from accreting than it does from having a continuum, then that would manifest as a veiling value of 1. Okay? So we see a range for these stars from 0.22, okay, that's some veiling, and all the way up to a whopping 7.5. That's a lot of veiling. So accretion can generate a lot of extra light. That's it for the spectroscopic analysis for those 10 stars. Now we're going to broaden our sample a little bit to include all the stars in that area for which we have photometry. So we don't have our own spectra for all of it, but we do have the photometry. So yeah, 21 still young stars we're thinking about, if you think all the way back to that early slide, the ones that were marked in blue, which we just looked at, the additional ones that are marked in orange, which were selected from an X-ray survey. It's a good test of youth, but doesn't always give you accreting stars. And also the weird pink guy that was over off to the side. Okay, so yeah, the goal here is we're going to want to get how bright these stars are, how intrinsically bright. We already have temperatures from the spectral types. We just got that. So if we have temperature, and we get a luminosity, how bright the star is, we can then plot these stars on everybody's favorite HR diagram. Hooray! So HR diagrams plot luminosity versus temperature. They are a very good way for, they're a very good way to analyze the evolutionary stage of your star. So here's just a plot showing the models. Luminosity versus temperature, temperature versus luminosity, luminosity versus temperature. I said that in the right order. Okay, the blue tracks are isochrones. So these show different ages, where the stars will be at different ages. At the top is 1 million year, at the bottom is, I believe, 100 million years, so close to main sequence. The gist from the isochrones is that young stars are a little extra bright. Then we also see the mass tracks, which is how the stars evolve over time. All of our stars are M and K. They're smaller mass, so they'll probably not change too much in mass. They'll kind of go straight down as they age. That's okay. But we want to know for sure. We want to know where they fall in that diagram, so that's why we're going to do this. Okay. You can't just take your photometry straight out of the telescope. You have to correct for things. You have to, if you're looking at stars, you have to get all the way down to the photosphere of the star. You want to get intrinsic properties of the star, not all the fancy stuff that's happening to it. So we want to sort of throw out what's happening from the accretion, throw out what's happening from the dust. We just want to say, we want to see just the star. So that's going to be called unveiling the star, to push aside the effects of the accretion, and de-reddening the star, which is going to push aside the effects of the dust that's in the disk, for example. So you can look at the formulas if you want, or you could be like me and you can look at the pictures. So it starts out like this, right? It's a star, it has a disk. It's a nice T-Tauri star. Might also actually have an outflow in that picture. We're going to ignore that. So, as you can see, it's slightly blue, right? And it's very dusty. The blueness is an effect of the veiling, because veiling will tend to, because accretion is pretty hot, it will tend to give off more light in the blue wavelengths than in the red wavelengths. So overall, it makes the star look a little more blue. Okay, and there's also a scattered light effect. Yeah, overall, it just makes it more blue. Okay, so we want that to be pushed aside. We want to see the star under all of that. So we already measured the veiling. We know how much extra light that veiling's giving off, or the accretion is giving off. So we take it away. So bye-bye blueness, bye-bye a little bit of extra light. We end up with this. We've removed the effect of the accretion. But now we have all this dust in the way. We want to remove that too. The way you measure how much light you need to add back, in this case, is from the color of the star. Dust will tend to redden the star's light. It'll tend to scatter more of the blue light away and leave more of the red light. So based on how reddened it is, you can actually figure out how much total light was taken away from each of the different photometric bands. So that's exactly what we do. And then we add that light back. And then you end up with, hopefully, the photosphere of the star, more or less. So that's perfect. We can do science with that. But this is how bright the star looks from 360 parsecs away or so. We want to know how intrinsically bright it is. So now we need distances. Fortunately, Gaia's second data release has provided us with distances to 15 of these 21 stars that we're looking at. So that's great. We can make our calculations from that to get our luminosity, the intrinsic brightness of the star. Now, some of the stars, 6 of them, do not have distances from Gaia. What do we do with them? We assign them distances based on the stars that are next to them that do have the distances. So the ones that were all the way off to the side, the ones that were sort of the slower moving group according to radial velocity, there wasn't a lot of data over there. We just gave them all pH alpha 41's distance. Oh well, you do what you can. We just want to calculate a luminosity and see if it looks any good. The stars over by CG30, though, which actually turned out to be more interesting anyway, they all had similar distances to each other. So for the few stars in that group, all spatially close, some of them with similar radial velocities, for those that didn't have distances, we assigned them the average distance to the stars next to them. Okay? So we have our luminosity. Something else that Gaia gives us, proper motions. Proper motions are just the transverse motion of the stars, right, in space. We've already checked their motion towards and away from us. That's the radial velocity. Now we can check their 2D motion. And then you get three-dimensional velocity, basically, right? And that's good. If these stars are related to each other, we would expect them, again, to be moving through space together. So their radial velocities and their proper motions should all be similar to each other. Let's go ahead and check that. I'm going to lead you through this plot. This is RA and DEC once again, so we see where the stars are spatially. They're once again color-coded for radial velocity, just like before. But now we've added, as little arrows, we've added the proper motion. The arrow points in the direction of the proper motion, and its length is scaled to represent the magnitude of the proper motion. Notice it is enhanced a little bit so that you can see it, all right? So, whereas it would have been like this big on the plot if I did it at the actual scale, I bumped it up just for visual purposes to 10 times that, just so you can see it. Okay, so what do we see? The ones over by pH alpha 41, bit of a mess. Oh well, we'll let those go. These over next to CG30, that looks sort of interesting, doesn't it? We see a lot of arrows pointing in roughly the same direction with similar lengths. Oh, well, that's good. So all these stars by CG30, they have similar positions, they have similar radial velocities, they have similar distances, and now we see they have similar proper motions. CG30, this CG30 group, as I may call it, is very likely an association. So hooray, we found an association. It was previously discovered, really. It has, people have already looked into this one, but it's nice to confirm, and I think we've added a few members by doing this. Okay. So now that we know that it's a cluster, an association, now that we know it's an association, we can go ahead and plot it on the HR diagram because we have our temperatures from the spectral types, and we have our luminosities from the photometry we just did, the corrected photometry. Here are all the stars plotted on the model isochrones and mass tracks. Now I've rearranged color coding a little bit. The ones you want to pay attention to, the CG30 group, those are all in blue now, okay? CG30 group is blue. That's what we're concentrating on. And as you can see, several of them sort of cluster near that top isochrone there, the 1 million year isochrone. That means they're all probably young, just 1 million years. Some of them, there's some scatter. There are some large errors as well. Most of that comes from the variability in their magnitudes. So they're just a lot of these are actually variable objects. They'll be bright one day, a little less bright the next day. I think one of them had I think it was 3 magnitudes of variation or something. It was pretty bad. So that'll add to your errors, but overall we at least see they seem to hang around that 1 million year isochrone. So that's nice. Something interesting is happening over here, though. CG30 IRS4, that embedded object, it's all the way down here. Why is that? So that is a little bit odd. We are quite sure that CG30 IRS4 is associated with the other stars because it has that it has the similar radial velocity and it's spatially close, et cetera, appears to be by its lithium, it appears to be young, and yet it's all the way down here. So this happens sometimes. This actually happens especially with some stars that show moderate to high veiling. And CG30RS4 is such a star. It does have quite a bit of veiling. Sometimes veiling is associated with the light coming to us via mostly scattered light. For example, like HV tau C, which has a thick disk in front of it. That can cause you to collect mostly just scattered light from an object. Now, we don't know for sure because we don't have pictures of CG30RS4, not detailed pictures like this. But it's possible. If CG30RS4, which is embedded, is observed via mostly scattered light, and then if we took all that away by taking away the veiling, it might look dim on an HR diagram. That actually happens to the pink star next to it too, incidentally. possibly, which also show very high veiling. So maybe it belongs a little higher up than it looks. We're not sure, but that's our suspicion. Okay, let's look some more at CG30 IRS4. So here's its spectrum, all the way at the top in blue. We're comparing it here just to another young star spectrum, a standard young star, if you will, just to see that the features really line up. There it is. You can actually see features in CG30 IRS4, stellar features. So this is the first, really the first spectroscopically observed photosphere of a star embedded specifically in a cometary globule. Looks like just to the side or in front of. This one's inside, maybe because it looks very embedded. So this one's inside. Okay, so how did this embedded star turn out? How did it measure up? Surprisingly, it doesn't seem to show very protostellar-like characteristics. It actually looks a lot like the other T Tauri star. Its H-alpha width was relatively low. In fact, it's officially a weak-line T Tauri star, which is possibly non-accreting. So it seems to already have gathered most of its mass. And also, its rotation was only its projected rotation was only 6.3 kilometers per second. So it seems already a T Tauri star just by these properties. But it is associated with CG30, the gas. It is associated with the cometary globule itself, according to the radial velocities. Those do match, so that's nice. Because they match, and because we have that group of stars next to it that seem to also have radial velocities that match the velocity of the gas of CG30, we actually have a distance now, thanks to all these stars. We have a distance to the cometary globule CG30. And that's actually sort of nice. We didn't have distances to these before. People were always saying, oh, they're in the Gum Nebula, 300, 400 parsecs, I don't know. This is better. Now we actually have a real distance to it, so at least we got that. Okay. So now that we're happy with our little association there, we're confident that the CG30 group is an association, we can go ahead and get its accretor fraction. I'll remind you, that is the number of stars that are accreting in a region divided by the total number there. Okay? So in a region, a quiescent region, that's just forming stars from a big collection of gas and dust, a big molecular cloud, such as Taurus, pictured here, you're going to expect at a young age, at about, well, this one's 1.5 million years, but at about 1 million years, you'd expect an accretor fraction of about 50%, roughly. Half the stars there are accreting, the other half might still have disks, but they might not be accreting anymore. What do we see in the CG30 group? If we count up all the stars that are accreting and divide by the stars that, well, just all the stars there, we find that the accretor fraction is actually quite low, 21 to 36%. This is despite how young this region is. This region looks like it's about 1 million years old by the lithium and by the HR diagram. So it's interesting that so few of the stars there appear to still be accreting. Could this be an effect of the high radiation environment? Maybe. It could also be an effect of selection bias. Maybe. And now I'll explain that. So I mentioned that those 10 stars that we observed with Keck, those were selected because of broad H-alpha. If you're picking stars because of broad H-alpha, you'll tend to find the stars that are accreting. But we had 21 stars total, right? So for that second section, we added other stars in the region that were selected for their X-ray luminosity. When you pick stars for X-ray luminosity, they'll probably be young, but they'll actually probably not be accreting anymore. So we have these two different selection methods. They do have some overlap between each other, and we do use both. So we're hoping that this number is still relatively robust, this 21 to 36% accretor fraction. We would like to check up on it some more, though. There are a few other stars in that area, according to Gaia, which just distance selected. There are some other stars there that we can look at. And it'd be nice to get their accretion properties too, and then have a more complete sample for an even better accretor fraction. So that's in the works. They're faint though, so we need a big telescope for those. Okay. So yeah, this is the central question of this whole study: is how does environment actually affect these young stars? We saw a low accretor fraction for CG30 area, where there's that strong radiation, much lower than the other region like in Taurus or Rho Ophiuchus, where you just have the collapse forming the stars and you don't have all this powerful radiation being pumped onto them. So yeah, we want to know how this affects everything that's related to the stars. How does it affect, for example, the star formation rate? How does it affect these stars as they come into the T Tauri phase and start to form planets? If it really does disrupt the disks early, that would probably upset the planet formation process because you just don't have as much time anymore. So that'd be something really interesting to look at in this region. Some other things we can get by studying the stars near these cometary globules is we can actually get distances to them. That hasn't been done before, so it's nice to do that. And we can get just young star properties as well. See how they're doing in that environment. Okay. Oh, spoiler. So I've looked at one. I've looked at CG30, right? I've looked at the stars near CG30. One high radiation environment sample. I need to grow my sample. So I need to find other stars by other cometary globules in the Gum Nebula. How the heck do you do that? Well, I've developed a little tool called Cluster Finder. It is now available on GitHub if you want it. Hooray! And all it does is, it's still available. It's still there. Anyway, I've already used it, so who cares, right? So, so this is just a nice little tool in Python that lets you empirically hunt for clusters in a bunch of Gaia data, okay? So here it is. It just plots right ascension versus declination, just shows you where the stars are. And it color codes, you have a choice. It color codes for distance, or proper motion in RA, or proper motion in DEC. You get to toggle through those as you see fit. And what you get to do is you get to take this horrible mess that comes straight out of Vizier, and you get to make some cuts. So the first cut I'm going to make is, well, this is for the CG30 region, just as a test of concept. You can make proper motion cuts and distance cuts, and also Gaia error cuts. So some of the items that have too large errors, too large for your purposes in Gaia, you just throw them out, right? So first, let's just go ahead and make a proper motion cut, because we just studied this region. We have an idea of more or less what the proper motion of the stars associated with CG30 should be. Oh, that's better, all right? So this is color-coded for distance. If stars are associated with each other, we expect them to be at about the same distance as each other, which will manifest in this plot as they'll all be the same color, all right? So do we see a blob of stars that are close to each other that appear to be the same color? I've rigged it. They're in the middle, and they're turquoise. Yeah. So we already see, oh, what's that little blob? What's that little same colored blob? Like it's like coloring. You just do this until the colors look nice. So now we can make some more cuts, this time distance cuts and error cuts. So anything from Gaia that had a large error, throw it out. And also distance cuts, we're just kind of zeroing in on, based on the color coding, where that cluster seems to be. And then look at that. That's pretty clear. So here we have this little blob of stars that have similar distances and similar proper motions. Well, that's good. Maybe they're in the same location in space. Maybe they're moving together through space. Maybe they're associated, right? So that's how I find clusters. And you can plot them up, make them look pretty. And because it's from Gaia, you can also get a color magnitude plot. Let's go ahead and do that. So here are some more models. These are isochrones from Padova. Here's the 1 million year, and I had to use Padova because I needed the Gaia magnitudes just to make this easy. So this is Gaia blue versus Gaia blue minus Gaia red, okay? So the green isochrone there, that's the 1 million year isochrone. And then the bottom one, that's 1 giga-year isochrone, so like more or less main sequence, okay? Yeah, main sequence, great. So here are the CG30 stars that passed the cut test. And yeah, they hover around. This is with no corrections. They hover around the 1 million year isochrone. So we look at that, we say, okay, maybe that's a cluster and maybe it's young. Great. Maybe it's a good candidate to observe. We already did this one. We need to find some more. I have gone through probably like, well, all of the cometary globules that are are visible in that little ring there. All the close by cometary globules. That's like 27 out of those 32. I've looked around all of them just with this quick empirical method. And so far, in addition to CG30, I have found 6 candidate young clusters. So this is exciting for a number of reasons. For one thing, it means I have more regions to study in the same way that I studied CG30. And for another thing, these are new clusters. I checked the catalogs. They don't appear to be in the catalogs. So if you need to look at open cluster stuff, I guess you can borrow these, because here they are, and people haven't looked at them yet. I plan on looking at them, though. So first one we're going to study, this one's a little bit closer. This one's at about 290 parsecs, still within the Gum Nebula, solidly within the Gum Nebula. It's nice because it's closer, it's a little bit brighter. So we can study that with, with a telescope that's smaller than Keck, and that's nice. We're also going to look at CG22, and that one's about 360 parsecs, similar to CG30. Yeah, we just want to see what's up with these. So, yeah, that's enough. Okay, fine. Okay, so once again, the goals as we study these, we want to figure out, are these clusters young? Are they accreting, right? Are they associated with each other, these stars? Are they associated with a cometary globule? And then, if we're happy with that, we find, yeah, these probably are associated, we want to calculate that accretor fraction and see how that compares to other star-forming regions, such as Taurus or Rho Indicus. Okay. So, the tool of choice this time, big thanks to Todd, is Chiron. We're going to be... Oh, and Wei Chun. Yes, you're right. A big thanks to Todd and Wei Chun is we will be studying these stars. Leonardo. And Leonardo, you're right, because you did you did all the reduction. He's the king of Chiron. Yeah, okay. A big thanks to Todd and Wei Chun and Leo. Thank you so much. And Hodari. He actually helped me normalize them, so yes, and Hodari. And why the heck, and Russell, and my parents, and Jesus, and my boyfriend. Anyway, moving on. We're using Chiron to study these young stars. So Chiron is on a 1.5 meter telescope. It has a resolving power of 25,000. So Keck was 34,000, this one's 25,000. This is still enough to hopefully get a reasonable measure of the radial velocities to see whether or not these stars have lithium and to check out the H-alpha emission, the possibility of H-alpha emission. So yeah, optical range, that'll include our H-alpha, that'll include our lithium. We're happy. So the first one we're doing is CG1. Here is its color magnitude diagram. Now this is one of the older, apparently, one of the older possible clusters in the bunch. But it's also the closest, so we're just going to go ahead with it. It's still a new open cluster. It'd be good to see what's going on in there. Also, we might still get a distance to the cometary globules. And who knows, this might be a good place to look for planets. So still definitely a region of interest. Let's jump right in because we have these spectra. Okay, so what am I showing here? I have lithium here. I have H-alpha here. Well, right away we see, oh, no emission. That's too bad. Oh well, they are older. This is sort of to be expected. They look older anyway, and this sort of confirms it. They probably are older. So, not much emission here, but we actually maybe see some lithium, which is sort of interesting. And those up there, I'm pretty sure they're maybe G or K type. So, they still seem to be maybe young-ish, right? Yeah. It's also possible that, like I said, we can still maybe get a distance to the cometary globule, and we can still find out some other neat stuff. So let's look at them. Maybe a little emission there. I don't know. Yeah. Yeah, they're pretty nice. Hopefully we can get some radial velocities for these. I'm still working on that. The code ran, but it looked weird, so I still have to... I'm still troubleshooting. It's in progress. Okay. So next on the bucket list is CG22. Bucket list? No, it's not a bucket list. Next on the to-do list. I don't want to die. CG22, okay? So this one's nice because, oh, it looks like it's quite a bit younger than CG1, so it is certainly of interest. I noticed that they seem to follow them in the what is that? The lower mass range of these stars. They seem to follow the isochrone, and then in the higher mass range, they kind of don't. I noticed that for all of them. Maybe it's Padova's problem, maybe it's just weird. I don't know. We're working on that. But anyway, the ones that seem to cluster around here have apparently been younger. CG30 clustered around there, so maybe this is younger, and we'd definitely like to take a look. This is already queued in Chiron, so fingers crossed that it'll show some neat stuff. Hopefully some lithium, hopefully some emission. So yeah, that's this is my immediate plan here. I got to finish analyzing the spectra from CG1, and then hopefully soon start analyzing the spectra from CG22. We also want to grow our catalog of spectral standards. All right, so we have a few observed under the same conditions as CG1 and CG22, but we want some more. So we're working on that because it'd be nice to get all those spectral types to compare to and just have more nice spectra to compare to. Get better radial velocities, et cetera, and better temperatures. Okay, then the next plan after that is we're going to try to move some of these to, well, we want to observe all of them with Chiron if we can, but some of them are a little more faint, so we're going to probably try to move up to Goodman. We're going to try to propose to Goodman and observe with, that's a 4-meter telescope, so see what we can see with that. And then maybe I'll find some more. I'll keep playing with Cluster Finder if it hasn't actually been removed from GitHub. It hasn't, it's fine. We'll see if we can find some more, and then I have to write paper number 2. It exists, but it's not very far along yet. It has like 3 paragraphs, just like Wikipedia, and headings. Okay. So here's the grand plan, because I'm at university now. So big checklist. Let's just go through it fast. Some of these things I've actually already done. So I've already submitted the first paper. Yay. And I'm working on the second. Yay. And we've already actually observed CG1, and we're about to hopefully observe CG22. And then I just need to analyze them. So that's the part that's done, and then the rest, hopefully it will come along. So working on it. Here it is if anybody needs to know anything. Okay. So in summary, I have spent a good bit of time looking at stars in a high radiation environment. A big goal is to see, does that affect said stars? These are all by cometary globules, which only form in high radiation environments, so it's a good place to study, well, star formation in high radiation, triggered star formation. We want to know, is that radiation maybe disrupting the circumstellar disks? Is it having any other effects? We want to know. So yeah, I'm doing that. I've done it to 1 cluster officially. I'm working on doing it to more. And in the process, I've actually found some new open clusters. That's about it. Here are these if anybody needs them, and I'll leave this up.